Good afternoon, myself Maninder Kaur, lecturer chemistry. Today my topic is gas laws. Gas is one of the three states of matter, the other two being liquid and solid. A gas differs from a solid and a liquid in a number of ways. A gas fills entire space available to it and therefore it has no definite shape or volume. Gas, it has no definite shape or volume. The molecules in a gas are in a continuous motion in all possible directions in the complete space available within the container in which it is enclosed. The molecules in a gas are in a continuous motion in all possible directions in complete space available within the container in which it is enclosed. The average velocity of gas particle is 15,000 meter per second at ordinary temperature. Substances that are gases under normal conditions. First is helium. Its formula is He. Second, neon, Ne. Argon, Ar. Hydrogen, H2. Nitrogen, N2. And nitrogen monoxide, NO. Oxygen, hydrogen chloride, HCl, ozone, O3, ammonia, NH3 and methane. Its formula is CH4. Some important industrial gases. First is methane. Origin and its use is natural deposits and domestic fuel. Ammonia from N2 and H2. Uses in fertilizers and explosives. Chlorine. Electrolysis of seawater, bleaching and disinfecting. Next is oxygen, liquefied air used in steel making. Ethylene, its formula is C2H4, high temperature decomposition of natural gas used in plastics. Characteristic properties of a gas. Gases do not possess any definite shape or volume. They will completely fill all the space available to them. Gases, they don't possess any definite shape or volume. The tendency of a gas to fill the available volume within the container is the result of the freedom that gas particles have to move everywhere in the available space. This freedom of movement of gaseous molecules is due to weak binding forces. This freedom of the movement of gaseous molecule is due to the weak binding forces. In other words, their intermolecular forces are very weak. Expansibility. When pressure is applied on the gas, it contracts, and when pressure is released, the gas expands. When pressure is applied on a gas, it contracts, and when pressure is released, it expands. When the temperature is increased, the particles gain more energy, move faster, and move away from each other. When temperature is increased, the particles gain more energy, move faster, and move away from each other. As a result, the intermolecular attraction becomes less prominent. The volume of the gas increases. Low density. Since gases have large intermolecular spaces, they have very large volumes. Since gases have large intermolecular spaces, they have very large volumes when compared to their masses. Thus, they have low densities. Solids exert pressure only in downward direction. Solids exert pressure only in downward direction. Liquids, they exert pressure downward as well as to the sides, and gases, they exert pressure in all directions. This pressure is due to the bombardment or the particles against the walls of container. This pressure is due to the bombardment or the particles against the walls of the container. 4 physical quantities of gases. First is pressure. Its symbol is P, and SI unit is Pascal. Other unit mm, Hg, torr. Volume. Second is volume. Its symbol is V, meter cube. Temperature. Its symbol is T. Unit is Kelvin, centigrade, Fahrenheit. Moles. Its symbol is N. SI unit mole. States of matter. There are 3 states of matter. First is solid, second is liquid, and the third is gaseous. Each of these states is also known as phase, and the matter that are present in these are considered as the part of these phases. For example, heating of ice will change it from solid phase to liquid, or further heating would change into gaseous phase. Picture of states of matter: solid, liquid, and gas. Three states are interconvertible by changing the conditions of temperature and pressure. Solid changes to liquid on heating, and further heating it changes to gas. Gas on cooling changes to liquid and further changes to solid. Solid state. The classification of matter into solids, liquids and gases is termed as physical classification of matter. In solids, constituent particles like atoms, ions or molecules are mostly closely packed and have the strongest intermolecular force of attraction. In solids, the particles like atoms, ions or molecules are closely packed and they have strongest intermolecular force of attraction. Liquid state. The liquid state lies in between gaseous and solid state, as there is neither the ordered arrangement like in solids nor the complete disorder of constituents as in gas. It is generally observed that the properties closely resemble those of gases, while a few characters match those of solids. In the light of kinetic molecular theory, liquids may be regarded as a continuation of gases into the region of small volumes and high intermolecular attraction. The cohesive forces in the liquids have been stronger than those in gases, and that keeps these molecules confined to a definite volume. The position of molecules in liquids are not fixed. The position of molecules in liquids are not fixed. At the same time, these forces are not strong enough to entirely eliminate the movements of the molecules in the liquid. At the same time, these forces are not strong enough to entirely eliminate the movements of the molecules in the liquid. Gaseous state. In 1654, Otto von Guericke performed Magdeburg hemisphere experiment to show that the air exerted pressure and put the foundations for modern concept of gaseous state. Properties of gases. Gaseous particles are of two classes. They are intensive and extensive. The properties that depend upon the amount of gas, like mass and volume, are called extensive property. The properties that depend upon the amount of gas, like mass and volume, are called extensive properties. while in uniform gases where the properties are independent of amount like pressure and temperature are called intensive property. The properties are independent of amount of pressure and temperature are called intensive property. What is a gas? A gas is a sample of matter that conforms to the shape of container in which it is held and acquires a uniform density inside the container. Gas acquires a uniform density inside the container even in the presence of gravity and regardless of the amount of substance in the container. If not confined to a container, gaseous matters, also known as vapors, will disperse into space. Perfect gas. A perfect gas is a theoretical gas that differs from real gas in a way that makes certain calculations easier to handle. Its behavior is more simplified as compared to an ideal gas. In particular, the intermolecular forces are neglected, which means that one can use ideal gas law without restriction. One can use ideal gas law without restriction and neglect many complications that may arise from van der Waals forces. Ideal gas. An ideal gas is a theoretical gas composed of a set of randomly moving non-interacting point particles. An ideal gas is a theoretical gas composed of a set of randomly moving non-interacting point particles. The ideal gas concept is useful because it obeys the ideal gas law. The ideal gas concept is useful because it obeys the ideal gas law, a simplified equation of state. Ideal gas equation PV is equal to nRT. P is pressure, V is volume, N is number of moles, R is gas constant and T is temperature. So, the ideal gas equation is PV is equal to nRT. Gas laws. First is Boyle's law. P1V1 is equal to P2V2. Charlie's law. V1 over T1 is equal to V2 over T2. Gauss-Lussac's law. P1 T1 P1 over T1 is equal to P2 over T2. Gas laws. First of all, we will discuss Boyle's law, second Charlie's law, and third Avogadro's law. First is Boyle's law. Gases undergo similar change with the change of temperature and pressure. According to Boyle's law, the product of pressure and volume of a given mass of gas is constant at constant temperature. According to Boyle's law, the product of pressure and volume of a given mass of a gas is constant at constant temperature. Thus, if the volume V1 and pressure P1 of a given mass of a gas are changed to V2 and P2, the temperature remains constant, then P1 V1 is equal to P2 V2 at constant mass and temperature. So, according to Boyle's law, the product of pressure and volume of a gas is constant at constant temperature. Boyle's law gives the inverse relationship between pressure of the gas and its volume. If the pressure of the gas is doubled, the volume of the gas seems to get reduced by half. If the pressure of the gas is doubled, then the volume of the gas seems to get reduced by half. If the volume of the gas is doubled, then the pressure of the gas is reduced to half of the original. The volume of a given mass of a dry gas is inversely proportional to its pressure when the temperature remains constant. The volume of a given mass of a dry gas is inversely proportional to pressure when the temperature remains constant. Robert Boyle discovered this law in 1662 and it was named after him. It can be restated as the product of the volume and pressure of a given mass of dry gas is constant at constant temperature. The product of volume and pressure of a given mass of dry gas is constant at constant temperature. P pressure inversely proportional to V at constant temperature. So, PV is equal to K, where K is constant. Let us assume that at a given temperature, a fixed mass of a dry gas has its volume equal to V1 and pressure equal to P1. At a given temperature, a fixed mass of a dry gas has volume equal to V1 and pressure equal to P1. Without change of temperature, if the pressure is changed, the volume also gets changed. Without changing the temperature, if the pressure is changed, the volume of the gas also gets changed. Then the new volume be V2 and the pressure will be P2. According to Boyle's law, P1 into V1 is equal to P2 into V2 is equal to constant. The pressure and volume can be altered any number of times without change of temperature. The pressure and volume can be altered any number of times without change of temperature, but still the product P into V remains constant, but still the product PV remains constant. So, P1V1 equal to P1V1 is equal to P2V2 equal to P3V3 equal to P4V4 equal to K at constant temperature. This is also known as Boyle's law demonstration. Boyle's law equation. According to Boyle's law, pressure is inversely proportional to volume of the gas at constant temperature. According to Boyle's law, pressure is inversely proportional to volume of a gas at constant temperature. This can be expressed as P is inversely proportional to V. Pressure is inversely proportional to volume. When the proportionality is removed, a constant is used. So, pressure is equal to constant over volume. When the sign of proportionality is removed, a constant is used. So, the pressure is equal to constant over volume. It can also be shown as pressure into volume is equal to constant. It can be shown as pressure into volume is equal to constant, or P into V is equal to K. K is constant. If K1 is given the value of constant, then PV is equal to K1. If K1 is given the value